So, our speaker today is Bartosz Kwaśniewski.
Very good.
Thank you. And he's going to talk about the title you see there, Non-Commutative Cartan C subalgebras. Please, Bartosz, go ahead.
Okay, thank you. So maybe I will shoot. Okay, I have a plot here. So thank you for the invitation. It's my first time in Argentina, so I'm very happy. I haven't been there. And so since I was invited to this non-commutative geometry seminar, I decided to give a talk on this non-commutative Cartan subalgebras. So I thought it will fit to the topic of the seminar. And I kind of suspected that the participants of the seminar will not be that familiar with the topic. So I presented it in a more non-detailed way. So I hope not all participants will get completely bored during the talk. So the talk is based on my joint paper with Ralf, but I will mention also some other results from my other papers with Ralf. And the talk was supposed to be a kind of gentle introduction to this non-commutative Cartan business. Okay, so let me start with history, which will be also a plan of the talk and the motivation, I suppose. So it all starts with the beginning of the operator algebra theory. So in 1940, von Neumann introduced what is now called the von Neumann cross product. So for a discrete group action on a measure space, he constructed this von Neumann algebra, these cross products, to produce factors. So these are factors whenever such an action is metrically free, meaning that the set of fixed points by the action has measure 0, and the action is irreducible in meaning ergoic. So this metrical freeness is important. I mean, so this metrical freeness can be characterized in this way, that this is the general form of a commutative von Neumann algebra. So, but this commutative von Neumann algebra on which the action happens, in fact, is a maximal abelian subalgebra of this cross product. So soon it was realized that that from this inclusion of this maximal abelian algebra into the cross product, one can recover at least orbits of the action, if not the whole action. So in fact, in 1971, Vershik noticed that, and then Feldman and Moore developed this theory in more detail. So they introduced this Cartan von Neumann subalgebras, one could say. So what is this? So this is an inclusion of von Neumann algebras here. So do you see my cursor or not? I'm not sure. Should I point?
I see it. I see it.
Okay, good. So this is an inclusion, maximal abelian inclusion of a von Neumann algebra into a non-commutative von Neumann algebra, which is regular and has a faithful conditional expectation. And then they show that this, in a sense, is in a one-to-one correspondence with a measure equivalence relation on this measure space. So meaning that having such a measure equivalence relation, one can always construct such an inclusion. And if you have this inclusion, then you have this measure equivalence. And if the inclusion is isomorphic, then the measure equivalence is isomorphic. It's like a complete invariant for such inclusions. But I want to talk about sister algebras. And of course, this is inspired also like approach, sister algebraic approach. And Kumjan introduced what he called sister diagonals. So these are maximal abelian inclusions of sister algebra. So this is a general form of abelian sister algebra. So these are discontinuous functions on X vanishing at infinity. Satisfying a bunch of axioms, he managed to prove that these such inclusions correspond to principal et al. Hausdorff groupoids. I didn't mention there is a twist here and there, but I will tend to ignore the twist in my talk unless you ask me about it. So principal groupoid means, in essence, I mean, so principal groupoid is just an equivalence relation. So in a sense, he characterized this kind of topological, there is a topology, I will mention it soon. But that was like a too strong maybe condition. This was not corresponding to metrical freeness, but rather to freeness. And it was Renault who kind of gave this slightly more general definition, but embraces all the important examples. So he introduced this notion of Cartan C subalgebra. So this is an inclusion of a maximal abelian algebra in B, in a sister algebra B, satisfying a bunch of axioms. I will soon present them. And he proved that such inclusions correspond bijectively to topologically principle groupoids. So topologically principle means that up to sets of empty interior, this is principle groupoid. Or now I would call it like, I prefer to call these kind of notions topological freeness than topological principality. So this is like the right replacement for this metrical freeness, or this measure equivalence is this topological equivalence kind. Okay, and this is very important. This is a very important result. So in particular now, recently Xin Li proved this result that every classifiable simple sister algebra contains a Cartan subalgebra. And this, together with this result, implies that any classifiable simple sister algebra, so this means any sister algebra, simple sister algebra which you can put your hands on, that you can see, has this model, this groupoid model. Okay, and it was very soon, I mean, 3 years later, I mean, I'll give just the dates of publication. So Rui introduced this very nice definition. I mean, so he tried to generalize this to the non-commutative setting where the small algebra might be also non-commutative. So he gave this very nice definition, but he managed only to, I mean, this is all what is in his paper. So he only proved that any such inclusion comes from a certain Fell bundle over inverse sine group. So this is this replacement for the groupoid. But he did not specify what kind of Fell bundle is this, and he didn't give like any non-trivial examples, non-commutative examples of this. So he gave us nice condition, but it was not easy to recognize it on some examples. And so this is this sneaky snake of non-commutativity. And it took some years, I mean, and it came out from my work with Ralf. We worked on these non-triviality conditions, that somehow we were working on these conditions, we were able to find nice characterizations of this of Rui's definition in several terms. In particular, this gives us lots of examples. So the plan of the talk is as follows now. So I will recall a bit of this theory, then I will very briefly recall Rui's definition and try to very briefly describe all these conditions that appear here. So what is this purely outer closed for bundles? Okay. No questions. Everything is easy. So throughout the talk, I will consider these inclusions of sister algebras. A is a small sister algebra, B is a large sister algebra. Some authors prefer the other orders, I mean the other notation, sorry for this. So Kumjan introduced these normalizers for sister algebras. So these are those elements in the bigger sister algebra that when we conjugate elements in a smaller sister algebra, then this conjugation leaves the smaller sister algebra invariant. So in this way, conjugation with this BB star gives us this like a completely positive mapping on A, and we have a kind of like a generalized inverse of this mapping, so we can conjugate in the other direction. And we will also always assume that this inclusion is regular in the sense that it has a lot of these normalizers. So it is often said that the inclusion is regular if the sister algebra generated by these normalizers is the whole B, but it is easy to see that these normalizers form a semi-group. So you might take a product of normalizers, you will get a normalizer, and they are closed under involution. So a sister algebra generated by normalizers is just a span. So we assume this, and we also include in a definition of regularity this non-degeneracy condition. So this thing here says that the approximate unit for A is an approximate unit for B. So for abelian inclusions, David Pitts showed recently that this is superfluous, this is automatic. For non-commutative inclusions, I'm not sure whether this is known.
Sorry, one small question. When you write AB, you mean the sums of products, the completion of that, just the products?
You mean here?
When
Here is
AB. No, AB, the capital AB.
Here.
Yeah.
It doesn't really matter, but yeah, you may take whatever you want to. Everything is equivalent. So you may take, soon it will be important, and then I will use this notation to denote like the closed linear span of the products.
Okay.
But for this condition, any way you think about it will give you the same thing. Okay. So if you don't like non-unital case, this just means that if A is unital, this just means that the unit of A is the unit of B. So yeah, I could restrict to the unital case here, but yeah. So this is a definition of Renault definition of this Cartan inclusion, this abelian inclusion. So an inclusion of sister algebras is Cartan if the smaller algebra. So we always assume that it's regular, and this is Cartan if the smaller algebra is maximal abelian in the larger algebra. And we also want to have this faithful conditional expectation. So conditional expectation, the fastest definition is just a norm one projection from B to A, then it is automatically completely positive and A by module map. And faithfulness means that it sends non-zero positive elements to non-zero positive elements. So the primordial example comes from diagonal matrices. So if we take A to be matrices, diagonal matrices, so we have only entries on the diagonal and zeros everywhere else. So this is well known. This is a nice exercise from linear algebra, that this is a maximal abelian subalgebra of the algebra of all matrices n times n. And this is obviously regular because whenever you take a matrix entry, any matrix entry will be a normalizer of this algebra in this way. And any matrix is a span of matrix units. This is kind of like a discrete example, but it is a really good example. And another example comes from cross products. So for a discrete group action on a locally compact Hausdorff space, we can form a cross product, the reduced cross product. So by definition, it is a completion of this span of these elements of this form, where A is a function from this function living on X, this continuous function, and UG is a certain unitary representation of the group. So all these elements of this form are normalizers. So I identified this algebra with the subalgebra of the cross product by writing U1 for this neutral element. I identified functions here with functions multiplied by this universal element corresponding to the neutral element of the group. So then it is easy to see that all these are normalizers. So we have also this canonical faithful conditional expectation that sends sums of elements of this form to this element corresponding to the neutral element. So the only lacking element from the definition is that this inclusion is maximal abelian. So this inclusion coming from the group action, from the cross product, is Cartan if and only if this smaller algebra is maximal abelian in the larger one. And then this is very well known that this is equivalent to topological freeness of the action. So I would call the action is topologically free if the set of fixed points for the action, so HT is the homeomorphism corresponding to the group element T that forms the action. So that the set of fixed points for these non-trivial elements of the group have an empty interior. So this is very well known. In fact, this was already observed by Ralf Meyer. He introduced his twisted products. So I think this is the first time where this topological freeness condition in fact appears. I mean, he doesn't call it topological freeness. I think the name comes from Yama. And I also plan to discuss this groupoid picture. So maybe I will continue with my plan if there are no questions or suggestions. So X is throughout the talk locally complex. How to space what we may also identify it with this commutative system algebraic functions living on X. So yes, I want to generalize the previous example of these discrete group actions on a topological space. And this could be done in two ways, by allowing not group actions, but inverse semi-group actions, or by just moving to groupoids. And these two approaches are equivalent, and I wanted to briefly recall this kind of equivalence between these two approaches, so between the groupoids and inverse semi-group actions. So there is a question, no, just a comment in the chat. Groupoid is just a small category with only invertible arrows. So I also view these units of this category as these identity arrows. So I identify identities in this category with elements of the groupoid, and it is topological whenever there is topology on this, and such that all these operations that you use in this category are continuous. And the groupoid is étal whenever there's ranged domain maps or local homeomorphisms, when I treat this X as a subset of G. So in particular for étal groupoid, the space X is an open subset of G. Local homeomorphism means that these maps are open and locally injective. Other way how one could phrase this étalness is that it has a cover by bisection. So by bisection, I mean an open subset of the groupoid, such that the range map and the source map restricted to this bisection are injective. So if they are open, this means that they are like homeomorphisms from R of U to R of U and from U to D of U. And any such bisection determines in a natural way a partial homeomorphism on this space X. So this will give us this inverse semi-group action. So because D is injective on U, so we can move from DU to U, and then we can push it down by R. So in this way we can come from the set DU, the open set DU, to the set RU. So now we have an element in the set DU. It is a domain of a single arrow in U, and then this arrow sends it to this R of gamma, which is the resulting point for our homeomorphic HU. So in a sense, this partial homeomorphism is depicted in here. So I view this space X as a horizontal space, and arrows in G somewhat in this vertical direction. So this étal groupoid in the horizontal direction is topological space. It is very topological. I mean, it might be. And in this vertical direction, it is discrete. So this means that this étalness means that in this vertical direction, it is discrete. So this construction covers these group actions in this way. So we have a group action by homeomorphisms. Then we can construct this transformation groupoid, which is just a product and just product of X with G with naturally defined actions. So we view any pair XT as an arrow that starts with X and ends with HTX. So HT, these are those homeomorphisms from these actions. So in this way, we can encode a group action into a groupoid, and in a sense, we can go back, we can recover this action by looking at bisections, because for any group action, if we look at this set X times the singleton T, so G is discrete, so this will be like an open subset in this product, in the product topology here. So it's an open, yes?
Is your convention the usual one? I mean, are you that guessed that so it looks like T is multiplying itself. I mean, I don't exactly recall the convention of the groupoid of
Maybe I
I
missed the
imagine
convention here. I
that
mean,
you had t
yes.
minus 1 or something.
I mean, so yeah, you can do it in at least two different ways. I'm not sure which convention I use in the slide here. I mean, I think yes, it is okay, xt or not. So I can compose xt with hts. I think it is okay, even though usually one uses this convention going from right to left.
Okay.
And you could also view arrows by inverse, but I think this is I hope that there is no error on the slide. So if you look at this bisection, like this layer, t layer of this x and this product, and look at this a partial homeomorphism. I mean, in this example, this partial homeomorphism will be a homeomorphism. So one recovers this HT. So in this way, looking at this action of these bisections, one recovers the action. So this general ideology. So moving from group actions to étale groupoids, just replace this group elements by these bisections. So in particular, if this groupoid is a group, so it acts as a singleton, then bisections are just singletons. So then bisections are just group elements. So these bisections recover the group. So in general, bisections, they do not form a group, they form an inverse semigroup. So I will consider only unital inverse semigroups here. So this is a unital semigroup such that, so it will be an inverse semigroup if any element T has a unique, this T star, this generalized inverse, right? So these are these relations familiar for those who work with partial isometries. Also, the difference between the inverse semigroup and the group is that, I mean, so whenever we have this product T star T here, this relation tells us that this is an idempotent. So in an inverse semigroup, we have a lot of idempotents. In the group, we have only one idempotent, which is this neutral element. So this is similar to the difference between groupoids and groups, that in groupoids we have plenty of identity elements. So partial homeomorphisms form naturally an inverse semigroup. So by partial homeomorphism, I mean homeomorphism between two open sets. And if we define the composition of such partial homeomorphism in this way, that this is the map that is defined on the largest domain, that the composition makes sense, then it is a semigroup which has no inverses in general, but it has these generalized inverses, and this will just be the inverse of the map from this codomain. So the H star will be the inverse of this homeomorphism from D to HD. So this is like a natural inverse semigroup, like a model one. So by an action, it is natural to consider the just semigroup homomorphism from S to partial homeomorphism of X. So this inverse semigroup action is just a semigroup homomorphism from the inverse semigroup to this model inverse semigroup. And for any such action, we may construct the transformation groupoid very much in the similar way as we have done it for the group. We need to just model out some elements coming from this because we have this plurality of multiple of identities. But there's this standard construction of the transformation groupoid. So any action can be encoded in this transformation groupoid, which is étale groupoid. And we can go back in the following way. So whenever we have an étale groupoid, then this set of bisections form naturally an inverse semigroup. So the product of two bisections you just define in this way. So we take these elements that are products of elements from U and V whenever the product makes sense. And if this natural generalized inverse, this involution is just given by the inverse of arrows. And this gives us so this by this G is an inverse semigroup, and it acts on the unit space by this partial homeomorphism that we discussed on the previous slide. So this gives us an action. So whenever we have a groupoid, we have this action by these bisections, and this we can use this action by this inverse semigroup of bisections to recover the groupoid, because the transformation groupoid of this action by bisections is G. So in general, we don't need to take the all bisections. We only need to take this inverse subset group, which is wide in the sense that Rui, I think, introduced first, but I don't think Rui gave this name to this notion. I think it was, maybe it was Rui with Enrique. Okay, so these are very well known facts. I think most of you know them very well. So when we have this tall groupoid, then we can construct the star algebra. So this is the space, we consider the space of continuous compactly supported functions on G. So because we assume our groupoid is tall, this is the same. We could view this space as span of these functions that live of bisections. So I identify the spaces with functions on G. So whenever a function is on U, when U is a subset of G, I just put 0 elsewhere. So every such a compactly supported function is just a finite sum of elements in this of such functions living on bisections. And the standard formulas, meaning the convolution product and the involution given that, as you can see, defines the star algebra structure on this CC of G. So because this is a tall groupoid, so in fact this sum is finite. So it runs over all etas such that this product makes sense. But in fact, apart from finite number of etas, this will be 0. So this makes sense. This is a nice defined star algebra. And there is a nice completion of this star algebra that gives us the reduced groupoid star algebra. So there is this maximal and the reduced one. We are interested in the reduced one. So there are plenty of definitions, but the definition that will work for us is that we complete this space in a norm such that this restriction maps, whenever we have this function on G and restrict it to X, this gives us a well-defined map because we assume Hausdorffness, maybe I should have said that. And we want to complete this in a norm such that this map is contractive and faithful. So then by the very construction, we have this conditional expectation, which is faithful. These functions on X, they embed into this reduced cross product as a subalgebra. And all these functions that live of bisections, then they are normalizers for this inclusion of this C0 of X into the reduced groupoid sister algebra. So again, this is a regular inclusion with a faithful conditional expectation. And when applied to this transformation groupoid for the group action, one would recover here this reduced cross product. Also for matrices, the picture looks like this. So any equivalence relation can be viewed as a groupoid, and with this groupoid structure defined by these two simple formulas. So whenever we consider this full equivalence relation on this discrete set of n elements, and apply this construction to this groupoid, then we recover just matrices n over n. So if we plug this product, this groupoid product into this formula, then we'll recover just the matrix multiplication here. And this is just this matrix taking adjoints of a matrix. And then this inclusion of the C0 of X into the reduced algebra recovers this inclusion of diagonal matrices into the algebra of matrices. So here is the celebrated result of Jean Renault. So he characterized this. So these abelian Cartan inclusions, they are in a bijective correspondence with étale groupoids with a twist. So what does it say? The result says that whenever we have Cartan inclusion, then the small algebra is of course commutative because it's maximal abelian. It is commutative algebra on the unit space of some étale groupoid, étale Hausdorff groupoid, which is topologically free. So this topological freeness is exactly what is needed for being maximal abelian again. And moreover, this groupoid and the twist are uniquely determined by the inclusion, meaning if you have two isomorphic inclusions, then these groupoids are naturally isomorphic. So in this way, this is bijective correspondence. Okay, one more thing maybe I should say I didn't say about this Hausdorff-ness. So for étale groupoids, the space X is always an open subset of G, and it is also closed subspace of G, if and only if the groupoid is Hausdorff. So this Hausdorff-ness gives us, in fact, this expectation, because when you restrict a continuous function to a closed open set, you will get a continuous function. Without this Hausdorff-ness assumption, this might not be continuous. So then things are more tricky. Okay, so this is this commutative part. Sorry for this, for those who know it very well. And I wanted now to pass to this non-commutative part. So as we have seen, these étale groupoids, we can view them as inverse subgroup actions. And this is like, this could be a hint of how we would like to replace now this étale groupoids with something non-commutative, because if we want to move to non-commutative inclusions, then we need to forget about the space X, and the usual thing one does is replace the space X by an algebra. In my case, this will be an arbitrary sister algebra. So what is a non-commutative counterpart of a étale groupoid with a unit space being just the sister algebra A? One could just rewrite this by considering inverse subgroup actions on a sister algebra by partial automorphism, and this makes sense. This theory exists, is well developed, but since we also want to include twists and all this stuff, it makes much more sense to replace these étale groupoids in a non-commutative setting by inverse subgroup actions by Hilbert bimodules, and by this action by Hilbert bimodule. These actions go by the name of Fell bundle over S. So yeah, I will now talk a bit about this non-commutative structure of inverse subgroup of Hilbert bimodules. So now, I mean, so this is this lemma. In essence, this all lemma is hidden in Ruij's work. We just took it out from Ruij's paper with Ralf. So here now A is a small algebra, it's a sister subalgebra of B, but now it is an arbitrary sister algebra. So we have this inclusion, and in such inclusion, in fact, generates certain inverse semigroup. And if this is regular inclusion, then this gives some inverse semigroup grading. This is what I would call an inverse semigroup grading. So whenever you have this inclusion of sister algebras A and B, which is regular, meaning that it has a lot of these normalizers. So we consider, we take this S to be the set of spaces. So M is a closed linear space consisting entirely of normalizers. And it is also A by module. So whenever we multiply M by A, we land in M, and the same from left and right. So these are like Banach A by modules, whose elements are normalizers of A. And this forms naturally an inverse semigroup with operations inherited from B, meaning whenever we take two elements of these two bimodules and we consider the closed linear spans, then this is again an A bimodule in this class. And taking the star, this also does not takes us out of S. And we also have these relations that are important for the definition of an inverse semigroup. So yeah, so
sorry,
yes.
do you impose those relations? But I mean, you only consider those M's that satisfy that, or do every such M satisfy that?
I consider only M's consisting of normalizers, such that M is a closed linear space and it is A bimodule.
And then automatically you mean that, and for such M's, this inverse in the semigroup sense.
I mean, so yeah, maybe I should make it. yeah, maybe I should make it more precise. So consider this S of this form. So these are the spaces. Elements of this S are these spaces. So one can show that whenever you have these two spaces, then their product is also the space of this form. So this is a semigroup. And you have these relations, and this M star is the unique element in this S such that these relations hold. And this M star is given by the star from B. So this is an inverse semigroup. So S given by this is an inverse semigroup. Naturally, this is a natural inverse semigroup. So in fact, I mean, there are plenty of points of view now because it follows from these relations that those M's will be Hilbert bimodules, A bimodules naturally, because whenever you take product M star, you will end up in A. And the same with M star M, you will end up in A. Also, these kind of relations would recall to some people something what is called the ternary ring of operators. So all these N's are also ternary rings of operators. So there are plenty of points of view here. But for me now, what is important is that S is an inverse semigroup. Naturally.
Bartosz?
Yes.
I mean, do you actually need a M contained in M? And I mean, the last two conditions in the definition of S, aren't they automatic as well?
I don't think they are automatic. But yeah. So the model example would be if we consider like a groupoid picture, right? So for groupoid picture, so normalizes, I mean, so functions even on bisections would be normalizes. So we take any bisection. Yeah, but maybe this is not a good example because
the reason is that reason is that if you look at a single element in M and you do M star M, then that is in A by definition, right?
Yes.
So you can use the polarization condition to deduce that this condition holds for every pair of elements. So M star N. Well, I think it works. I think it works. Maybe it's not.
Okay.
Yeah.
I mean, that would be nice. I mean, so I think that this definition appeared already, like at least in two of my papers. So it would be nice if I could make it shorter. So thanks for this remark. Yeah, I'll think about it. But yeah, one would need to think about it because this might be delicate. So in fact, all these things that I wrote here are true even without this regularity assumption. This holds for any non-degenerate inclusion. Regularity assumption just gives us that the whole B is just a closed linear span of this M. So by an inverse semigroup grading, I mean that kind of thing that is written here. So I mean that we have a family of spaces indexed by an inverse semigroup such that the product of these elements in these spaces is consistent with the product in the inverse semigroup. Here, this is given for free because the product is in S is just the product of spaces. But in a sense, I think that this lemma tell you like a lot about the structure, what is going on here. So now what we, yes?
One thing, usually when one talks about gradings, one expects to have a direct sum.
Yes, that's true. That is why I call it inverse semigroup grading. And that's why Ru in his paper, he calls this Fred grading because he didn't like this name grading because of this reason that you said. So for groups usually one wants to, I mean, this one imposes this condition that the elements, the fibers of the grading are linearly independent. I mean, so here they will be in a sense. I mean, one need to take into, maybe I will show the next definition and then try to explain the issue. So in a sense, this group grade, in a subgroup grading, I want to impose this this kind of independence. But since an inverse semigroup elements are not totally independent because we have this natural preorder, I need to kind of make this condition slightly I will maybe show the definition. So this is like a very brief definition of a fell bundle over inverse semigroup. This was developed by Nando Zieben and then by Rui. So S is an inverse semigroup with unit for simplicity. So a fell bundle over S is a family of Banach spaces. So these are these fibers. They come with the structure of Banach spaces, and we have these multiplications that BG and BH are mapped. Two elements are mapped into BGH. So this is this consistency with the semigroup law. And we have these involutions that turn element in BG into this element BG star. So this star is this star from the inverse semigroup. And we also have these inclusion maps. So we want to have these BGs to be included, embedded into BH whenever G is smaller than H. So in this inverse semigroup, we have this lots of idempotents that define this partial order. So G is not greater than H if there is an idempotent such that H times this idempotent is G, so we can restrict it. So in the group case, there is only one idempotent. There is only identity is the only idempotent. So this, in the group case, this can happen if and only if G is equal to H. And here we need to, so this is responsible for this independence. So I want them to be independent, very kind of, I want them to be dependent when the semigroup elements are dependent. And if and only if, in fact, I want to have that.
I see.
Yes. So this must satisfy this natural axiom. So if I form this sum such that I identify this element from BG with BH whenever this happens, then I can complete it in a C-star norm. So I will not give you details. I will just rely here on the authority of James Fell. So this is first volume of his book. I mean, with Torah, of course. And so, but what one needs to know from this construction is that these axioms are such that the unit fiber of this fell bundle is always a C-star algebra, and all these BGs are Hilbert A bimodules, and that embed naturally into a C-star completion of this construction, and I want to consider the reduced C-star algebra. So I mean the completion with certain, yeah. So the definition of the reduced C-star algebra here is also not easy. I think that Rui was the first one to give it, and then there was Rui and Alcides Bus and Ralf Meyer who clarified this definition for the saturated gradings, saturated full bundles. But yeah, so in the setting, what we want, I will give you maybe I will try to explain this definition later. So now once more we have this inclusion when A is an arbitrary C-star algebra. So so I want to get to Rui's definition of non-commutative Cartan subalgebra. So original definition was that A was a maximal abelian subalgebra, and Rui's way of thinking was that, I guess, that it can be characterized in this way, that this maximal abelianness can be characterized using commutants like this, so that the commutant of A and B is contained in A, and A is commutative. So if A is commutative, then this condition is equivalent to being maximal abelian. So what Rui just looked at first was that just forget about this commutative. So we just want this condition that this commutants of A and B are contained in A. This makes sense for arbitrary C-star algebras, but it was kind of not enough. So another kind of crucial remark here is that notice that one can phrase this condition in terms of bimodule maps. So once again, if we have this commutant of A and B, then this map sending A to A times V is an A bimodule map. So that this is A bimodule map just means that that V is a commutant of A and B. Because then it doesn't matter when we multiply by A from left or right, because we can move A.
So sorry,
you're lost.
So the commutator of A
Yes. So V commutes with all elements.
A subset of B.
So V is an element of B, and it commutes with all elements in A.
Yeah, but so, I mean, when you define the commutator, you define it with respect to an inclusion of A in some algebra. And yeah, and A is already included in B. So why do you need to intersect the commutator?
Yeah, so this is maybe confusing. This was supposed to clarify things, but maybe it confuses things. So when we take the commutator of A and B, so this was just that V is in B and it commutes with A. Yeah, because you could consider this like B embedded into a larger algebra. So this is not like a commutant in the sense of B of H or something like this. This is the commutant of A in B. So because this is this commutes with A, then this map is a A by module map. So such maps, this is what we call the virtual commutants, such A by module maps. So once again, this condition that A prime intersected with B is contained in A is the same as saying that each of these maps have range in A. So this maximal abelianist condition now is translated into language of A by module maps, that each such A by module map has a range in A. This was the way of thinking, I guess. So here's the definition. A virtual commutant is this A by module map, but in fact, we needed more than just maps defined on A. So these are maps defined on any ideals. So these are like partially defined maps, A by module maps. So this is, so this is confusing. A virtual commutant then is just by definition A by module map defined on an ideal in A, taking values in B. And then with this notion of a virtual commutant, the definition of a non-commutative Cartan subalgebra is as follows. So if we consider regular system inclusion, it is a non-commutative Cartan inclusion if any virtual commutant has range in A. So this condition is supposed to play a role of this condition. And we have this faithful conditional application. So yeah, this is Rui, but we have him line. So and what will prove that whenever we have this non-commutative Cartan inclusion, then that there is this natural Fell bundle over inverse same group. In fact, this is this Fell bundle coming from this lemma that I showed you, and this B is naturally isomorphic to the cross-sectional, this reduced cross-sectional algebra of this Fell bundle, and the unified of this bundle is A. So this inclusion comes from this construction, but there's only one way. And as you can see, it is not easy to imagine what does this condition look like in examples. So then the question that we wanted to answer, that we answered, is which Fell bundles give Cartan inclusions? Okay, so this is my last before. How much time do I have? Not a lot. So maybe I should hurry. So what we want to give answers is like, in a sense, this question consists of two questions. So first question is which Fell bundles give this this condition that any virtual commutant has range in A, and second is for which Fell bundles does this reduced cross-sectional algebra has a conditional expectation. So for the second question, the answer was known. And it was given by Alcides, Rui, and Ralf. So if we have this Fell bundle over inverse semigroup, then the condition that we need for the cross-sectional algebra to have a conditional expectation is that this action is closed in this sense that any fiber now of this Fell bundle can be split into this trivial part and non-trivial part. So if we embed this, if we treat this as this grading in the system algebra, then we can intersect this BG with A. So this gives us like a trivial A by module, and the condition says that this BG can be complemented by another A by module. So in general, this is not the case. we need to impose it to get the conditional expectation, and then the conditional expectation acts as follows. So it takes element of BG and it just gives you this thing. So it just cuts out this complemented part. So this is in a way given, this is how the conditional expectation now can be defined. So this corresponds to this Hausdorff-ness assumption for groupoids. And the second condition, there's no having non-trivial virtual idempotence, is just something that goes under the name pure outerness. But so we want this spellbound to pure outer in the sense that each non-trivial part is purely outer. And this notion of pure outerness for Hilbert by modules is now well established. So Hilbert A by module is outer if it is non-isomorphic to the trivial Hilbert A module. And it is purely outer if any restriction of A to any ideal is outer. So this condition is now well understood. And remark, so we could also kind of express these two conditions in terms of a groupoid, because any Hilbert by module induces by Morita-Riffel equivalence a partial homeomorphism on the spectrum of algebra. Here I mean irreducible representations, and this gives a transformation groupoid. So this BG acts by partial homeomorphism. We can construct the transformation groupoid, and then this action is closed in this sense that there is this conditional expectation if and only if this set A, which is open in this because this is an Natal groupoid, this set A is closed in this. So this explains the name. Why is it closed? Because of this. And outerness is linked with topological freeness by our work with Ralf. So if this transformation groupoid is topologically free, then B is purely outer. And you may come back sometimes. So if the algebra, the small algebra A is not far away from commutative, so this type 1, or if it is simple, then you can actually go back. So pure outerness is equivalent to topological freeness. But the main result is that the characterization of this non-commutative Cartan inclusion. So A subalgebra of B is non-commutative Cartan inclusion. If and only if B is isomorphic to this reduced cross-sectional algebra of a full bundle, which is closed, purely outer. So these two conditions characterize fully non-commutative Cartan subalgebras. And this results in the remark gives us a lot of information gives us tools to give a lot of examples now. So this fell bundle is unique, but only after some refinement, because this is like the choice of bisections in a groupoid. But this dual groupoid, this transformation groupoid, is uniquely determined by the inclusion. So any such non-commutative Cartan inclusion comes with this groupoid, which is unique. And now we can go to examples. So this is a most famous condition, I guess, for group actions considered in literature, for instance, for purely infinite cross products. So we have a discrete group action, which is topologically free in the sense of Archibald and Spielberg. So there are plenty of papers considering actions with this condition. Then the algebra A sits in the reduced cross product as a non-commutative Cartan algebra. So this means that all these papers that view this condition, they in fact deal with non-commutative Cartan inclusion. So there are plenty of them. So this is like one way. And another interesting fact that I want to end with is that when A, when A is commutative, this is one extreme case, and when A is simple, this is the other extreme case. So here we assume that the small algebra is simple, then the following conditions are equivalent. So I will just give you three. I could give you like those and not those. So the inclusion of a simple algebra in B is a non-commutative Cartan subalgebra under the assumption that the inclusion is regular, if and only if this algebra B comes from an outer full bundle over a group. So if A is simple, then this inverse semigroup, the underlying semigroup, has to be a group because idempotents in the inverse semigroup, they correspond to ideals in the algebra A, and now we have no ideals. So then the inverse group has to be a group, and this pure alterness is just alterness because there are no ideals. So then this full bundle and G are uniquely determined by the inclusion, and moreover, because we know that from our work with Ralf that when the small algebra A is simple, then alterness is the same as a periodicity, which implies detection of ideals and lots of other things. We know that if we have this non-commutative Cartan subalgebra, that not only A is simple, but also B is simple. And not only that, not only A and B are simple, but any sister algebra that sits between A and B is simple. This is what is called sister reducible inclusion. This was called by Rodam. So now there's a number of papers appearing on this subject, studying this sister reducible inclusions. So this corollary tells you that for regular inclusions, the structure is completely understood, and it comes with a group G and a full bundle over this group. So examples of this corollary are just this very well-known old example of Kishimoto, who proved that for a group action which is outer on a simple sister algebra, then the cross product is simple. So this is also a very highly cited paper of Kishimoto. Now we can say even more. So then this inclusion is sister reducible. So every sister algebra lying in between is simple. And also this is a non-commutative Cartan inclusion. And an example which does not come from group action, but from a full bundle maybe. So finally, let us consider the Kuntz algebra on two elements. So I recall that this is algebra generated by these isometries with orthogonal ranges that sum up to 1. Then the canonical anti-commutation relation algebra sits naturally in this. So this is the Cartan algebra is also the Glimm's 2 to infinity algebra. So this is a direct limit of this 2 to power n matrix algebras, but it is naturally isomorphic to span of this kind of oh no, the star is missing here. So this is this core subalgebra of the Kuntz algebra. And this is also a sister reducible non-commutative Cartan subalgebra, because this is simple. This is because this is a new UHF algebra, and this is a fixed point algebra of a circle action. So one can divide this O2 into the spectral subspaces of this gauge action, and then this has to be a periodic by the results of Algebra and Spielberg. So this means that it has to be a Cartan subalgebra. So also so this inclusion is also sister reducible. And I think I'm over time already, so thanks a lot.
So thank you for your nice talk. So yeah, so the car becomes, the car algebra has now a tan, so that it is a Cartan.
Yes, now car algebra is Cartan, yes.
Yeah. Now, is there a generalization of this that holds for, say, simple sister graph sister algebras?
So yeah, if you consider like this natural inclusions for graph sister algebras, for instance, like you take the algebra of functions on vertices embedded into the graph algebra.
Yeah,
then,
in the 0 degree part. I mean the part fixed.
The fixed point. Yes.
Yeah.
So for graph sister algebras, this is kind of, I mean, this example that I showed you, I could make it general. So for graph sister algebras, they all have this Z grading when the fixed point algebra is a subalgebra. So yeah, so if you want this to be, I mean, so this is like, so this will be so for graph sister algebras, this core subalgebra will be a Cartan subalgebra of this graph sister algebra, if and only if the graph satisfies this condition L, I guess. That every loop has no exit or entry depending on this.
Yeah.
So detection of ideals, because this is very specific, because for the group Z, For the group Z, there's detection of ideals is the same as a periodicity and all these other conditions. So that is why, yeah, in this example, I could like give you a nice answer, and this is the answer.
Okay. So are there other questions from the participants?
Could I ask a question?
Yes, of
Yeah,
course.
sure.
Yes. Cool. So, something that I wanted to understand was, so, part of the attraction of Cartan subalgebras in dynamics, right, is that it characterizes things on a dynamical level. Like you have this orbit equivalence in the Vauban-Moore theory and continuous. So what would it correspond to? Like, has anyone looked into this? Like what it corresponds to in the level of these non-commutative cartons?
I mean, so this is what I wanted to sweep under the carpet a bit. So here I just wrote that this is the unique after the refinement. I mean, so in a sense, related to your question, I guess, is what I wrote here. So for this non-commutative Cartan inclusion, you have this dual groupoid is always unique. So what is not unique is this S, because if you have this dual groupoid, now you could take, for instance, the inverse sine group of bisections of this guy, which will be larger than this S in general. So this refinement, in fact, means this. So what you do, you take this any field bundle over this inverse semigroup, and if you look at this inverse semigroup of this bisections of this groupoid, which is unique, and then you can kind of in a canonical way construct a field bundle over this larger inverse semigroup from this field bundle, and then for any field bundle that gives you this and that, this refinement is the same. But yeah, so this is much more subtle than for the commutative inclusion. But in the commutative inclusion, I mean, what you actually had, you had this equivalence of inclusions was corresponding to isomorphism of groupoids together with a twist. So groupoid, this is perfectly fine and perfectly understood. So this groupoid does not depend on the choice of this S. And that's all I can say in this framework. Of course, there are these rigidity results that go beyond this topological free case, because this non-commutative Cartan is somehow related to this notion that I really love, this topological freeness. So in this way, I think that we give answer. I mean, this is not very nice, maybe, but that's the nature of what we're dealing with. And if you want to go beyond topological freeness, then you kind of go beyond non-commutative Cartan. And then I don't know whether there is a work on this. Like, I don't know.
Okay, so are there any more questions? Perhaps is Owen satisfied with this reply?
I just want to apologize for my observation during Bartosz talk that I was a little bit confused about the axioms. So, I mean, please ignore what I said, because this is not, I somehow outlined the proof, but that proof is not correct.
Okay, I mean, yeah. Both ways it would be nice to if I can shorten definition, then it is nice, but on the other hand it would be stupid to have it in at least 2 papers already published if that can be deleted. So,
yeah, I mean,
thanks.
I just noticed that it is in my original paper as well.
Yeah, this is what I thought. I didn't have time to check.
Yeah, sorry.
It's okay, and thanks for being there.
Okay, so if there are no more questions, I will stop the recording now. Okay.